Alright, so I've created 50 videos, 50 PowerPoints on the topic of domain adaptation, also domain generalization, also universal domain adaptation, also source-free domain adaptation. But all of them are on the problem of domain shift. There are three things that may cause domain shift: covariate shift, label shift, what else? Concept shift, and sometimes our technique automatically and implicitly resolves all of these problems. So let's focus on this paper in 2014, Deep Domain Confusion Maximizing for Domain. When we say domain invariance, it means that when we go from source domain to target domain, we want the domain to be invariance, the probability distribution to be the same. So you know a background about domain adaptation. In machine learning, unfortunately, we always assume that we have IID samples from a very complex distribution, but it is wrong. We should know that, for example, in source domain, we have a distribution, and in target domain, we have another distribution. So there is a shift, for example, in self-driving cars, when we move from normal weather to snow weather, then we have a shift in our distribution. All features are changed now, so they may get classified incorrectly. So let's focus on this paper in 2014. Oh, by the way, we have unsupervised domain adaptation, supervised domain, semi-supervised domain adaptation, universal domain adaptation, source-free domain adaptation. And the domain generalization assumes that we have multiple domains. So also it has a different concern. But I should say that the biggest problem in domain adaptation is an unsupervised domain adaptation, not supervised or semi-supervised. And so these are great papers from these amazing researchers. So what you see is not what you get because you have domain shift. And it's a major limitation of deep learning, because in deep learning you assume you have access to IID samples, which is wrong. They are coming from different distributions. Some of them you have huge data sets, some of them you have data scarcity, so it's not fair. Also, this topic is also related to privacy issues, because you can always share models, but you cannot share data. So that's a different story that people talk about. Federated domain adaptation, privacy, and those things, that we ignore that. Because here we don't talk about information privacy and the federated learning. Recent reports suggest that a generic supervised deep convolution neural network model trained on a large-scale dataset reduces but does not remove dataset bias on a standard benchmark. Fine-tuning deep models in a new domain can require a significant amount of data, which for many applications is simply not available. So we propose a new convolution neural network which introduces adaptation layer and an additional domain confusion loss to learn representation that is both semantically meaningful and domain invariant. We additionally show that the domain confusion metric can be used for model selection to determine the dimension of an adaptation layer and the best position for the layer in the CNN architecture. So you see, you have fully connected adaptation layer, and we have domain loss here. Your source are labeled images and the target is unlabeled images. The domain loss should be minimized. So this idea is for 2014, so it's not very mature. Nowadays we have much more detail. And you see, if you want to maximize domain confusion, by the way, there are many ways that you can measure this discriminancy between a source domain and target domain. One of them is maximum mean discrepancy. The other thing could be adversarial methods. And there are many methods, many paradigms for domain adaptation. But this one traditionally is used, maximum mean, even in 2014. So we consider 2014 is the same year that GANs was discovered, generative adversarial network, which I've explained in the playlist for generative AI and synthetic data. So here, to minimize the distance, we consider the standard distribution distance metric, which is maximum mean discrepancy. This distance is computed with respect to particular representation phi, this phi. Here on the target, here summation is on the source. So we define a representation which operates on source data points and on target data points. Then an empirical approximation is like this. But we know that it has good properties related to kernel learning and many things. So not only do we want to minimize the distance between domains or maximize the domain confusion, but we want a representation which is conducive to training strong classifiers. Such a representation would enable us to learn strong classifiers that readily transfer across domains. So this is your classification loss, standard loss that you use on the available label data, because you have the ground. This is ground truth label. But this MMD is just the distance between the source and the target data. And of course we have a hyperparameter because it's a trade-off between these two different losses. But how do you choose the adaptation layer dimension? Before we can learn a new representation via our proposed fine-tuning method, we must determine how wide this representation should be. Again, we use MMD as the deciding metric. In order to determine what dimensionality our learn adaptation layer should have, we train a variety of networks with different weights in Amazon 2 webcam. So this is a sign that we are saying that we are going from source domain, which is Amazon, to the target domain, which is webcam task.